で見る効果検証入門です。AI 事業本部 AI ラブのByambadalai Undralと申します。今日の内容は英語で発表させていただきます。So today I will discuss the estimation of distributional treatment effects in randomized experiments. Since this presentation is aimed to be introduction to distributional treatment effects, here's what we will cover today. So first, I will start by explaining the concept of randomized experiments, also known as A/B tests. And then next, we will explore how to estimate average treatment effects, which is a commonly used method for evaluating the impact of different treatments. And after that, we will move beyond averages and learn how to estimate distributional treatment effects, providing a more detailed understanding of treatment impacts across the distribution. So finally, I will discuss how machine learning techniques can be used to estimate distributional effects with greater precision. Okay, so let's go into the first topic, which is an A/B test. So what is an A/B test? So A/B tests are also known as randomized experiments or randomized controlled trials or RCTs. And these are considered the gold standard in causal inference for determining cause and effect relationships. So while there is a lot of data available out there, it can be really challenging to isolate causal effects from observational data. And so randomized experiments provide a controlled environment that allows us to clearly assess whether one factor directly causes another. And so in today's data-driven world, many companies across many industries use A/B tests to inform their business decisions. And these tests are particularly popular in tech companies where A/B tests are being used to help optimize products, features, and user experiences. But the use of randomized experiments extends beyond the tech industry. They are widely applied in fields such as medicine and social sciences. So for example, in medicine, RCTs are crucial for evaluating the effects of vaccines or medications on various health outcomes. And in social science, randomized experiments are being employed to understand the impact of various interventions, such as educational programs for children. So these examples highlight the importance of A/B tests in many different domains. And so let's look at an example of an A/B test from Abema, our streaming service. So Abema's phone app allows users to easily watch their favorite shows and anime and things like that. And when users open the app, they are greeted by the home screen. Okay. So now the question is, what should we display at the top of this home screen? Should we feature some promotional content that users might enjoy, or should we show them a sponsored advertisement in that space? So we are interested in determining the value of promoting this content, some content, versus showing an advertisement. So specifically, we want to know, does displaying this promotional content increase users' viewing time? So to answer this question, we need to conduct a controlled experiment. In an ideal world, we would like to observe, how users could behave in both of these scenarios. But since that is not impossible, we cannot observe these two different worlds. We can use an A/B test where users are randomly assigned to either a treatment group or a control group. And in the treatment group, people can see a content promotion, and in the control group, people can see an advertisement. Okay? And so by analyzing these results, we can assess how these different approaches affect users' engagement and overall viewing behavior. And so here's what the home screen looks like when you open the Abema app on your phone. So for people in the treatment group, at the top, we display this content promotion, whether it's like a show or an anime that users might enjoy, followed by some other recommendations below that. And for the control group, at the top, we can display a sponsored advertisement, followed by other recommendations below that. So now, to evaluate the effect of these two different approaches, the key is we randomly split users into treatment group and the control group. And the randomization here is really the key, which ensures that the groups are comparable to each other. So if you, with the large number of users, these both groups should be similar on average in terms of their demographics and behaviors, allowing us to fairly measure the impact of the content promotion versus sponsored ads. Okay? So here is what the flow of the A/B test looks like. So first, we run the experiment. So in the Abema example, in treatment group, users see content promotion when they open the app. And in control group, users see a sponsored app when they open the app. And we run this experiment over some specified period of time. So this could be just one day, or it could be like an entire week, or it could be for an entire month. Okay? So once this experiment concludes, what we do is we go back and then collect the data. So first we observe the outcomes. In this case, the outcome we are interested in is the viewing time of the users, how much they are viewing specific contents. So we will observe these outcomes, and then we compare the results in these two groups. So by comparing the outcomes of the treatment and control groups, we can assess the effect of showing this content promotion versus an ad. So finally, in the last step, these insights gained from this experiment will guide future business decisions, helping us better understand how we should optimize the home screen for better user engagement. Okay. So now let's go into the next section of how we compare these outcomes. Okay. So the most common way to compare outcomes between the treatment and control group is the average treatment effect. Okay? So in a randomized experiment like the one we have, the calculating the average treatment effect is very straightforward. So we actually simply take the difference between the average outcome that we observe in the treatment group and the average outcome we observe in the control group. Okay? And so in this Abema example, the outcome is viewing time. So the average treatment effect will tell us how much more or less time on average users in the treatment group spent watching the content compared to the control group. Okay? And so in the graph on the slide here, I'm showing an example of how the data can look like. So the purple is the outcome that we observe for the treatment group. So all the data that we observe, we can plot all the viewing times of all the different users. So it could look something like that. And for the control group, we plotted with a blue color, and it's showing also on the same graph. And what we are doing here is we are looking at we're taking the average of all these different data points, and we are simply looking at the difference between these two averages and say that this is the effect of this particular treatment. Okay? So this is the most common way to evaluate different treatments. So now, while this average treatment effect is useful, it has some limitations. So the first limitation is that the average treatment effect does not account for heterogeneous treatment effects. So it doesn't account for individual differences between these users. Okay? So every user is different, and people may respond differently to the same treatment. So some users might benefit significantly from some feature, but while others could experience negative effects. And so focusing only on the average is ignoring this heterogeneity within this group. And another issue that could arise when we only look at the average is when the average treatment effect is really small. It can be really difficult to detect statistically significant results. Okay? Because the average treatment effect is very small, the standard errors also need to be very small. And in the ABEMA example, for example, many users could have a viewing time that's very close to 0. If that's the case, that will pull the average down a lot. And so if a large number of users don't engage, then just looking at the average is going to give us just a very small number, which makes it harder to draw meaningful conclusions. Okay? So if this is the case, maybe looking at only the average is not enough. And so this motivates us to look at the distributional treatment effects to capture the full range of responses across users. So let's go on to the next section, which is about estimating distributional treatment effects. So now, instead of focusing only on the average treatment effect, we can now analyze a difference between entire distributions of outcomes. Okay? So this will give us a more detailed view of how the treatment is affecting different users. So to do this, we can use cumulative distribution functions, or CDFs. So the CDF, over here in the graph, we are showing the CDF for the treatment group and the control group separately. So the CDF at any given point, for example, this y point, shows the proportion of users with outcomes less than or equal to a certain value, this value y. Right? And so we can compute this CDF for various outcome levels. So in the ABEMA example, we can compute the CDF at the viewing time of starting from 0 to 1 minute, 2 minutes, 3 minutes, up until 60 minutes, or something like that, right? So depending on what kind of data you have, you can trace out the whole CDF, the cumulative distribution function. So now, by comparing the CDFs for the treatment group and the control group, we can see how the distribution of the viewing time is shifting due to the treatment. Okay? So now this approach provides insights into how different segments of users are affected rather than just how the average user is being affected. Okay? So another way to look at this distribution can be to look at the differences in probabilities. Okay? So the distribution functions that we just saw, the CDFs, can be used to examine differences in probabilities. So this leads us to the concept of probability treatment effect, which we call PTE. So the PTE here measures the difference in probability that the outcome falls within a specific bin, an interval. A bin is like an interval between y1 and y2, for example, as a result of the treatment. Okay? So for example, in this example, the first spin over here indicates how the treatment affects the probability of users watching 0 to 10 minutes of some content. Okay? So we can see that that probability has decreased in this graph. And the second bin over here is showing how much the treatment affects the probability of users watching 10 to 20 minutes of content. Okay, so that's the second bin, for example. So by comparing the probabilities across these bins for the treatment and control groups, we can understand how the treatment shifts the user's behavior in terms of specific time ranges, rather than looking at only the average effect, okay? And so, of course, we talked about the distributional treatment effect and probability treatment effect. We compute these quantities, and we also need to calculate the standard errors for these point estimates to draw statistically meaningful conclusions, right? So there are many ways to compute the standard errors for these quantities. But if you would like to get more precise estimate, what can you do? So that motivates, this question motivates our next section, which is about using machine learning methods to estimate distributional treatment effects, okay? And so before talking about the distributional treatment effects, let me talk a little bit about statistical significance and sample size. So to determine the statistical significance, we conduct some hypotheses, right? So a hypothesis can be something like the average treatment effect equals 0. In other words, there was no effect on average. So that is the hypothesis that we want to test. And if you want to do that, we need to calculate standard errors, right, on top of the average treatment effect. So when the standard errors are small, we say that these point estimates are more precise. Okay? So the point estimate that you get is precisely estimated if the standard errors are really small. So now, to reduce this standard error or variance, right, we typically aim to increase the sample size. If you have a lot of data, then the variance reduces and you get a smaller standard error and you get more precise estimates. However, increasing this sample size can be very costly. So you have to run your experiment for a longer time period, or you have to recruit more people. It is all costly. And sometimes it's not even feasible to do that, right? Depending on your setup. So this leads us to the question that are there any alternative methods to reduce variance without necessarily increasing the sample size, right? So this motivates our next slide, which is also the last slide in our talk. So this brings us to leveraging features or user characteristics, sometimes called pre-treatment variables, which you collected before the start of the experiment. Okay, so in our ABEMA example, these variables could include the viewing time of the users, the previous viewing time, and the age group of the user, or gender, or how much they use the app, or other engagement variables of this user. Okay? So now we can use these features to predict a binary outcome, indicating whether the outcome falls below a specific threshold y. So we will do this for many different y's, right? If you want to estimate the CDF over a different y or outcome levels. And so we repeat this exercise of predicting this binary outcome using machine learning methods for many different outcome levels. And then we use these predictions to now adjust our distributional or probability treatment effect estimates. Okay? So the key here is really that we are utilizing this information that we have about these users, and that is allowing us to reduce the variance of these estimates and making more precise, so that we have more precise estimates, leading us to more reliable insights. If you would like to learn more about more about the distributional treatment effects and more about using machine learning methods to estimate distributional treatment effects, you can look at our paper here. And the first QR code goes to our paper that we presented at ICML, the International Conference on Machine Learning 2024 this summer. This work is a joint work with Tatsushi Oka, who is a professor at Keio University and also affiliated with CyberAgent, and Shota Yasui from also CyberAgent. And on top of our paper, we also prepared a Python library, the Python package called DTE-ADJ, adjust. So here is the QR code. The second QR code goes to this Python library, whose maintainer is Tomo Hirata. And if you run an A/B test, and if you have this data that you collected before you run the experiment, you can use our library, which will allow you to plot the distributional treatment effects easily. And if you want, you can also use machine learning methods to get more precise estimates as well. So if you have more questions, if you have any questions related to the things I talked about today, you can contact me and my other co-authors through our email addresses. Okay, thank you. ご清聴ありがとうございました。